So with the drivetrain, we salvaged the motor and the gears from a RC car, and the motor is a 7.2 volt motor that spins at max 16,000 RPMs, and with 2-inch diameter tires, I can figure out the gearing and how fast it'll go. Alright, here we have the drive axle. You can see it was salvaged from another RC car. And here's the chassis, and it is made with salvage erector set pieces. The suspension has not been integrated or optimized yet, but this is roughly where the rear shocks would go. And then these are suspension links to keep the axles in line. Here is the steering that I developed for the car. The servo and most of these plastic pieces came from the salvage RC car, and I had to custom build these links to be the right length to actuate the steering.
Here we have the bulk of the electronics that I'm using for the RC car, where I chose to use an Arduino as the microcontroller because it's able to interface well with all the components, and above everything else, I'm the most familiar with that. And with it, for using my wireless communication, I bought 2 transceiver chips for the NRF24LO1s, and basically there's a library that I'm able to interface all my data with.
There's still a lot of bugs for me to work out with my wireless transceiver chips, but for the most part I'm able to send data from one Arduino to the other one without too much hassle. As you can see in this clip, one Arduino is actually taking input from a joystick and sending it out through the NRF chip, and it is being received by the other Arduino, where it then writes it to the wheels.
So here we have a motor driver circuit which I built in order to interface the power needs of the brush motors with the Arduino. As the Arduino can only push 20 milliamps of power, I needed a different way to address that. And so I took 4 in-channel MOSFETs and I basically pulse width modulate them so it turns them on and off very fast, and they behave practically like electrical switches at that point, and they move the motors at whichever desired speed I need them to.
Alright guys, so this is the embankment that I designed here. It's a 90-degree angle as for the specs, and it's made out of the blue board insulation. The bottom, the base of this actually is made out of the blue board insulation as well. It's adhered together, so the adhesive I used was a silicone-based caulking, and there was a few holes in the embankment that I had to fill, but I filled it with the expandable foam insulation, which didn't come out to be that much money. This is a river that I'm gonna put in there to add extra weight to this side because that side is actually pretty heavy. The actual pavement base here is made out of Vicor window flashing. I just use that because it's easy to paint on, which I'm planning on putting the red guard paint on it, which is a rubbery based paint.
Alright, so as a quick summary to what you've just seen, our civil engineer is on track with the embankment. It's looking very nice and we're ready to move on to the final stages. Our electronic components are all communicating with each other, and all of our mechanical parts are fully functional. But moving forward, we need to be integrating those and making sure that those are talking to each other to get our final vehicle design. And once that is complete, we can work on collecting data in the makerspace on each of our core segments. And that is what we're going to put into our LP, our linear program, which I now have fully functional and is up and running. And once we input that data, we can determine an optimal path, and we'll be using that for our final course run for prototype 2.